Hi, welcome to introductory session on microcontroller 8051 and integrated development environment Keel Microvision version 5, which we are going to use in our lab. Before actually we start programming in IDE, let's understand the key features of 8051 along with its architecture, pin diagram and its memory organization. Let's start with the architecture. This is a architecture of 8051 in which we can see there is a arithmetic and logic unit which actually performs all the operations. There are two registers, accumulator, that is register A, and a register B, which are closely associated with all the operations of ALU. Also, there is one register called program status word, which reflects the status of the execution. We are also provided with two on-chip memories, RAM and ROM. We have 128 bytes of RAM and 4 KB of ROM provided on chip. And also on the right side, you can see there are 4 ports, port 0, port 1, port 2 and port 3. All these 4 ports can be used for IO operations along with some special functions associated with them. Port 3 is having a very specific applications and functions for each pin of port 3. So we need a separate control signals and control circuit for port 3. Here you can see a memory organization in brief. This 128 byte RAM what we have, that is divided into 4 bank registers, bank 0, bank 1, bank 2 and bank 3, along with a bit addressable area and a general purpose RAM, which we will be seeing shortly in the coming slides. Here also there is a list of control registers which are called as special function registers, which are associated with the hardware operations as well as special functions. We will be discussing each one of them as and when we come across them in the programming. With this basic idea of architecture, let's see how this is packaged as a chip. Here you can see a pin diagram of 8051, which is in a DIP package, that is dual inline package with 40 pins. Pin number 20 and pin number 40 are used for biasing the chip, that is VCC and ground. Pin number 20 is ground and pin number 40 is connected to VCC, that is 5 volts. On the left side, you can see there are two ports, port 1 and port 3. Port 1 is a pure IO port. It does not have any special functions. Whereas in the port 3, we have a special function for each pin as we already discussed. So first pin, that is P3.0, is a RxD pin and 3.1 is a TxD pin. These two pins we are going to use for serial communication. The next two pins, 3.2 and 3.3, are interrupt pins, that is general purpose interrupts, INT0 and INT1. Both are low enable signals, that is active low signals, so they are indicated as INT0 bar and INT1 bar. The next two pins we have, that is timer pins. So they are timer interrupts, T0 and T1. And finally, another two pins of port 3 are control signals for memory operations. Then we have a two pins which are used for connection of external crystal, Xtal1 and Xtal2. Also on the left hand side, we are provided another pin, that is a reset pin, to reset the microcontroller. Now seeing on the right side, you can see port 0 and port 2. Port 0 is a multiplexed port and it does not have any internal pull-up registers. So this port 0 can be used as a data port as well as a address port. As I said, this is a multiplexed port, so both address and data can be sent over this port. So to identify whether the data or the bit stream which are there in the port 0 is the address or a data, we have one function called ALE, address latch enable. When this pin is enabled, the bit stream on port 0 is considered as the address, and when this pin is disabled, the bit stream on port 0 is considered as a data. So this address and data pins are used whenever we are connecting the external memory. Now for indicating that whether we are going to use an external memory or an internal memory, there is another control signal, that is pin number 31, external enable. So this enables or disables on chip memory. Whenever we want to use the external memory, we are going to disable the on chip memory. And similarly, we can enable or disable this particular memory. Then we have another pin, that is PSEN, program store enable, which is used to store the program in the external memory. Now finally we have a fourth port, that is port 2, which is used as a IO port. Also it can be used as an address port for a higher byte addressing. Now as we have two ports, port 0 and port 2 for external memory interface, so totally we have 16-bit addressing. That means we can interface up to maximum of 64 kilobytes of external memory. Now with this external memory and on-chip memory knowledge, let's understand a detailed memory organization of the data memory. So this is a data memory, that is RAM, we generally call, that is 128 bytes. Here, as we already discussed, that there is a 4 banks, bank 0, bank 1, bank 2 and bank 3. Each bank consists of 8 registers R0 to R7. So bank 0 extends from 00H to 07H of the hexadecimal addresses. Then bank 1 also consists of R0 to R7 register extending from 08H to 0FH. Similarly, we have bank 2 and bank 3, which also have 88 registers R0 to R7 extending from 10H to 17H and 18H to 1FH respectively. All 4 banks are having 8 registers named as R0, R1, R2, R3, R4, R5, R6 and R7. So now when we are programming, which register we are going to refer depends on 2 bits of program status word, PSW.3 and PSW.4. Those 2 bits are going to define which bank we are going to use. Now after this bank register from 20 up to 2F, we have something called as bit addressable area. That means each register can be addressed individually bitwise. Starting from bit 00, it can extend up to bit 7F. So totally we have 16 registers from 20 to 2F, which are bit addressable registers. Each register is having a 8 bits, so that makes it totally 128 bits. So each bit is also given a specific address starting from 00 up to 7F. Then after this bit addressable area, from 30 up to 7F, we have a general purpose RAM or a scratch pad. Then after this memory, that is after 7F, from 80 onwards up to FF, we have something called as a special function registers. Now, before going to the programming, let's understand brief about some addressing modes which are very important for the programming concepts. Now in 8051, there are 5 basic addressing modes which are supported. First one is immediate addressing mode. As the name suggests, the data required for the execution is immediately available in the instruction itself. Then we have a second addressing mode, that is direct addressing mode, in which the address of a memory location where data is available is directly mentioned in the instruction. Then third addressing mode, that is register addressing mode. Here the required data is available in one of the registers, that is R0 to R7. Then we have register indirect addressing mode, wherein register stores the address of a memory location where data is available. Then finally we have an indexed addressing mode, in which we have a base and offset addressing method, whereas the register A, that is accumulator, is used as a base address register, and DPTR, that is data pointer, is used as a offset address register. So adding these two values, that is base address value and offset address value, we are going to get a physical address. Now if you see the architecture going back, Here you can see the two registers DPH and DPL are shown as a part of DPTR. So this data pointer consists of two registers DPH and DPL. So DPTR can be completely used as a 16-bit register, or it can also be used as a separate DPH and DPL register. There's another 16-bit register, program counter, which stores the address of the instruction which is being executed. So this is required for conditional jump instructions and as well as unconditional jump instructions. Now with this brief knowledge on architecture, pin diagram and memory organization, let's start with the programming.